I'm just verifying that this is Tristan Miller. So I've already gone ahead and written out the problem statement as well as the corresponding images to the problem. So the problem statement reads, water is pumped from the large tank shown in the diagram below. The entrance to the pipe section is sharp-edged and the pipe is cast iron with a total length of 2 meters. Flow within the pipe is observed to be fully turbulent. The relationship between volumetric flow rate and actual head rise is provided in the pump specifications and is shown in diagram B. 1. Determine the volumetric flow rate for the system. 2. Show that the observation of fully turbulent flow was correct. And 3. If the pump is 70% efficient, determine how much power must be supplied to the pump. So from the problem statement, we know we're going to be using the Bernoulli equation. However, we're going to have to account for the head loss of the whole system pertaining to minor and major, as well as the head gain of the system due to the pump. And they specify material of the pipe as well as length and diameter, so we'll be good there. So from the picture, I've already indicated our points in question for the Bernoulli equation. We can see that both point 1 and 2 are open to the atmosphere, so we'll be able to cancel out both of those and put them to 0. We can say Z2 is at ground 0, so that can also go to 0. And point 1 is in a large tank, which that can also be assumed to be 0. And I'm going to continue. I'm going to solve for the head gain of the system because we have a relationship between head gain and volumetric flow rate as indicated down here in figure B. So I can solve for the head gain and able to get a relationship to the volumetric flow rate, which is what we're after in part A here. So we know that the head gain, according to our equation up top, will be equal to velocity squared over 2g plus the head loss minus z1. And we know, and I'm going to go ahead and solve for the head loss just to make this a little bit more simple, and then I will recombine and the entire equation down below. So we know that head loss is broken into major and minor, and this will look like friction factor multiplied by the length of the pipe times the diameter, the velocity squared over 2g, plus the minor losses, which is the accumulation of loss coefficients multiplied by the velocity squared over 2g. And I'm going to leave the friction factor as f for now, and I'll solve for that later. But we know from, figure 8.26 from figure 8.26, the loss coefficient for a sharp edge entrance is 0.5. So we know, and we also know, the length is equal to 2.0 meters, diameter is equal to 0.07 meters, and we have a common term, which is v squared over 2g that I can pull out as well. So we end up with the head loss is equal to f times 2.0, which is the length, divided by 0.07, v squared, 2g, plus 0.5 times v squared over 2g. And we can simplify this further. So we end up with HL is equal to 28.57 F plus 0.5, pulling out the common term, v squared over 2g. We are left with this, and recombining into the head gain equation from up above, we have head gain is equal to, again, v squared over 2g plus the head loss, which we just calculated. So I'm going to rearrange that to say v squared over 2g times 28.57 times the friction factor. Times the friction factor plus 0.5. And then we also have minus z1. And we can actually write this as, we can pull out another v squared over 2g. So this would be times 1 plus, in parentheses, 28.57 F plus 0.5. And we can go to the next page. And that will simplify further as well to the head gain is equal to V squared over 2G times, adding the 1 and the 0.5, you have 1.5 plus 28.57 F minus our Z1. And we know from this graph here that our head gain is also equal to 20 minus 2,000 Q squared. So we can substitute that in for the left side of the equation to try and solve for our volumetric flow rate, which is exactly what we're going to do. So we have 20, actually let me go a little bit higher, save myself some room. 20 minus 2,000 Q squared is equal to V squared over 2G times 1.5 plus 28.57 F minus our Z1, which is 6. Okay, and here is where I'm actually going to plug in for our friction factor. So we know, I'll put this in red here, that our equivalent roughness from, I believe it was table 8.1 for cast iron is equal to 0.00026 meters. And if we divide that by our diameter, 0.07, we end up with a relative roughness of 0.0037. And from Moody's, we get a friction factor approximately equal to 0.026. So from here, we can then plug in for our friction factor and subtract the 20 to the other side and begin solving for volumetric flow rate. So we end up with negative 2,000 Q squared is equal to V squared over 2G times 1.5 plus 28.57 times our friction factor that we just found, 0.026 minus 6. And I also, it will also be easier for us to multiply 2 by 9.81 meters per second squared here and simplify each term and multiply the V squared through. So this turns out to be negative 2,000 Q squared is equal to, oh, this should be minus 26 right here because I brought the 20 over. Okay, so is equal to 0.0509 V squared times 0.7428 minus 26. And that simplifies to negative 2,000 Q squared is equal to 0.0378 V squared minus 26. And we have this relationship between our velocity and volumetric flow rate. So we know volumetric flow rate is equal to Q over A. But in this case, we have V squared. So we can say V squared would be equal to Q squared over A squared. and we can calculate the area. Square. Coming out to 0.0038 meters squared. And plugging this in back into our equation is equal to 0.00378 q squared divided by 0.0038 meters squared minus 26. We end up with negative 2,000 q squared is equal to 2,556.304 q squared minus 26. And after solving for q, subtracting 2,556 from each side, dividing by that value and square rooting, we end up with q is equal to 0.0755 meters cubed per second. Oh my God. Per second. So that is our volumetric flow rate for this system, which is part A. And part B wants to know, going back to our problem statement, show that the observation of fully turbulent flow is correct. So in order to show that, we need to calculate Reynolds number. And we know that Reynolds number, if Reynolds number is greater than 4,000, we are turbulent. So Reynolds number can be calculated as velocity times diameter divided by kinematic viscosity. And now that we have our volumetric flow rate from the previous part, we can solve for our velocity, which is just equal to q over a, which is equal to 0.0755 meters cubed per second divided by our area, which we calculated above. And our velocity comes out to be 19.628 meters per second. So we can then plug that back in for Reynolds, and we end up with 19.628 meters per second times our diameter, 0.07 meters, divided by our kinematic viscosity of water, which is 1.12 times 10 to the negative 6. Excuse me, meters squared per second. And our Reynolds number comes out to 1,226,801, which is well above 4,000. So now that we have that, part C wants to know if the pump is 70% efficient, determine how much power must be supplied to the pump. Okay, so we know that efficiency is equal to the power supplied from the fluid, or by the fluid, divided by power supplied by the pump. Well, we have our efficiency equal to 0.70. And we want to solve for power required from the pump, which will be equal to power of fluid divided by our efficiency. And we know that the power required by the fluid is equal to rho GQ times head gain. So we can solve for power required or power supplied from the fluid in order to determine power supplied by the pump. Oh, but before we do so, note that head gain is equal to 20 minus 2,000 Q squared. And we now have a volumetric flow rate, so we can solve for this and plug it in to solve. So we have the power supplied by the fluid is equal to density, water, 1,000 kilograms meter cube. It's 9.81 meters per second squared. Times our volumetric flow rate, which is 0.0755 cubed per second. And that is also times 20 minus 2,000 times 0.0755 meters cubed per second squared. So this comes out to be power supplied by the fluid, 6,363.60 watts. But we want to know the power supplied from the pump. So that is equal to 6,363.60 watts divided by our efficiency, 0.70, which is equal to 9,090.86 watts is the power supplied by the pump. And that is this fluids problem.